Good afternoon, everybody. My name is Dario Trabucco. I'm the CTBUH Research Manager, and my primary activity at the Council in the past 2.5 or 3 years has been this research project sponsored by ArcelorMittal on the life cycle assessment of tall buildings. Anthony Wood and myself were the principal investigator for this research, but actually our role was to manage a much larger group of people, researchers, but also professionals and suppliers of materials, consultants that gave us a great support in achieving the results that we are going to describe today. I think that is a fundamental aspect of the research activities that we conduct at the CTBUH, because we are not people that like to work in our small offices at night doing our research and then disseminate it to the public, but we want to get the people that we are talking to engaged into the research in order for the results to be accepted by the industry and to be as reliable as possible. So the report authors include another group of people, of course, Olivier Vassart and Nicoletta Poppa from ArcelorMittal, but also Don Davis from MKA, who are contributing to this effort at a much bigger extent. But most of all, it includes another large group of people that I'm going to mention later, who really provided all the information that were necessary for this activity. So what was the objective of the study? The objective of the study was an assessment of the environmental impacts of structural materials and structural systems through the life cycle of a tall building. So the research was limited on the skeleton, let's call it this way, of the tall building. It didn't involve the facades. We're going to see something later. It didn't involve the internal finishes and the MIP, but it was what is up to date the most complete and detailed study on the life cycle assessment of a tall building. And that was made possible thanks to our sponsor, ArcelorMittal. So what does the life cycle of tall building mean? When we started to have to hear about sustainability in tall buildings, this was mostly confined to the use phase of towers, so to decrease the energy consumption, to decrease the water consumption, but that was limited from the first day that the occupant of the building enter into the building until they leave the building for any reason. This research was about everything that is described here. So from the production of the materials, the extraction of the raw materials, the manufacturing of the material, the internal transportation, to the delivery to the building site, the installation of the various steel, concrete, rebar, whatever, into the building, through the life phase, through the use of the building, and then to the end of life of the building, which is something that we don't really talk too much about, and we're going to hear a presentation afterwards. Life cycle assessment, we hear many times talking about this, but a life cycle assessment is the quantification and the evaluation is kind of an important thing, of the environmental consequences of different impact categories that a product, a process, a service, whatever, has throughout the whole life of that product or service, thanks to a scientifically accepted methodology. So in order to do this, the most important thing is to describe exactly the object that we are going to apply our research on. One of the parts underlined in blue were the impact categories results. So what does impact category mean? The impact category is somehow the target of the damages and of the, in some cases, of the good things that our actions have. In this case, we selected two very specific and important impact categories. The first one is climate change. So what effect the creation of this bottle of water has from the point of view of the environment, and in particular of the climate change. And then the other category that we decided to study and to focus our attention on was the depletion of natural resources. Water is a renewable product. The plastic that contains this bottle is not a renewable product, so we have to consider how much plastic do we have in the future. In the case of tall buildings, we're talking, and in the case of the structures of tall buildings, we are talking predominantly about concrete and steel. We decided to use 2 indicators. Of course, you can have many things that describe climate change. You can have many other aspects that somehow have something to deal with the depletion of natural resources. But what we decided to use were 2 indicators. One is global warming potential, so the effect on global warming, so on the heating on the environment that our actions have. And the other one is depletion of embodied energy. Embodied energy means all the energy that goes into the product during its production stage, during the manufacturing of the project, during the delivery of the project, and that it remains somehow embedded into the product also after it's been demolished and recycled or sent to a landfill. Tall buildings. So the focus of this research is the structural components of tall buildings. So in order to achieve some results that can be comparable, we had to select very carefully the object of the analysis. So we started from a real tall building in Chicago, 300 North LaSalle. We took the building, we took the general characteristic of the building, so the size of the floor plate, the inter-story height, some of the construction aspects of this building, and we decided to consider that and his big brother. So a tall building that's 120 story. So the target of this research is first applied on 2 different sizes of tall buildings. 60, the average building that we're now building in most of the cities, most of the capital cities around the globe, from the US to the Asian countries, and a 120-story building that, if constructed, will be the 5th tallest building, the 5th biggest building in the world. I'm saying biggest and not tallest because the original reference that we decided to use is a pretty bulky building. So if we expand this to a 120-story, of course, we have to enlarge the base, we have to create a bigger building. So the floor plate of this building will be the 5th largest of all. Then we declined, we decided to examine 8 different variations of structural configuration, considering concrete, steel, mixed, and composite materials. And in order to have, so this already gave us a 16 inventory of materials. The inventory of material is the recipe of the building structure. So how much concrete, how much rebar, how much steel profiles, how much studs, how much metal decking are needed to create each of these 8 by 2, 16 different solutions. Then in order to be more confident on the quality of the number, we decided to assign this exercise of creating the recipe of the materials to the most renowned structural firms around. And in order to be even more sure, we asked 2 of them to design the same building. So to have not just the numbers that we will have in a very, very preliminary stage of design, but also to have something more after a sort of refinement of the project, because we had to compare the 2 projects on the basis of the performances of the building. So we finally ended up having 32 different inventories of materials, so 32 different recipes, quantities of materials that go into the building. Candidates. So what were the structural systems that we decided to use? The first one was an old concrete structure, an old steel structure, so the 2 opposite structural use of materials, and then the combination of these 2 materials, so a concrete core and a steel frame, and a composite construction system. And when we have candidates, we usually have a winner. But I'm not going to tell you. You will find into this publication, which is the result of this research. You can find it at the CTBUH booth, and it contains all the information that resulted from this 2.5-year research activity. So this presentation is rather an instruction on how the results that are contained into this guideline should be considered. First of all, 2 very important things have to be taken into account. The first one is the recyclability. It's very important. Steel, of course, can be recycled, is a recycled and can be recycled material, and the characteristic, the mechanical properties of the materials that you obtain after recycling steel are exactly identical to the one of the original source of material. On the contrary, concrete is not recyclable. Of course, you can crush it and use it as a ballast, but the quality of the second life of the materials is not at the same, it doesn't have the same properties of the original concrete. So there are two different ways of considering the demolition of the recyclability of these materials. And of course, they have an impact. So we created this visual system to represent the results. So we started the year 0 of the building. We have, in the case that we use a recycled material, so steel in this case, but it will be also aluminum or other materials if that study was applied to other materials. We have an initial credit because we are using, an initial benefit, sorry, because we are using some materials that are recycled. Then, during the production process of the materials, we have, of course, an expense of energy and a release of pollutants because we are using energy to produce the materials. And then we have the life cycle of the building. We get to the demolition moment, and then we may take advantage of a credit. The fact that steel can be recycled in the future, here, give us a credit at the moment that we can use to make informed decision on sustainability. So there are two different schools of thoughts. One say, no, you can't consider. Somebody else say, yes, you have to consider. The reason for those that say no is that that is going to happen very far in the future. And okay, I might agree with this. And in fact, we considered a big number here in terms of life phase of the building. 70 years is quite a long time. But as we will see today, the demolition of tall buildings is happening more and more frequently. The extreme case was a building, 140-meter tall building in Singapore that was built as an hotel and demolished 14 years after the first stone was posed on the ground. So the life of that building was just 14 years. That's why we think that including the possibility of receiving a credit for what we built and from the future recycling possibilities is very important. And that's why the main results that are going to be presented in this research include also the credit for scrap. So you will see two different sets of results. As I said before, we considered two different impact categories and two indicators. One is global warming potential, and the other one is embodied energy. You will see the results in this study. I just want to mention about the fact that for each of these two different sets of results, you will see two columns, one marked in blue and the other one in green in this case. These two colors represent the fact that there are official data about the environmental consequences of the production of steel. There are environmental data about the consequences of the production of most of the material that go into a building. So not just steel as a raw material, but steel as a product. So profiles, decking, rebar, and so on. Unfortunately, there are no accepted data on concrete. So what we decided to do was to take the production, the average, or at least a representative production in Europe and a representative production in the US, and to use those two different values. And that's the reason why for all the scenarios, you will see that there are two different columns. One represents the average of the American concrete producers, and the other one, the average of the European concrete producers. So all the results for the 60-story tower are presented according to embodied energy and global warming potential. But then there is a second important fact to be considered. Steel can be used with carbon neutral energy resources. And this results in the fact, that the energy that is necessary to produce steel can come from a nuclear power plant, a hydroelectric power plant. And so the result of this is just steel. Of course, if you use other sources or the average electricity mix in most of the countries, you will have also a release of CO2, so a release of global warming potential. On the contrary, cement, concrete, and cement in particular, release CO2 as a consequence of the chemical process that transforms limestone into cement. So, yes, you may be able to use an energy source that is carbon neutral, but you will always have a release of carbon as a consequence of the chemical reaction that produces cement. And as a consequence, we wanted to see what is the environmentally optimized scenario that we can achieve. So if we go to ArcelorMittal and we say, hey, we want to buy your steel, but we want to buy your steel coming from a zero carbon plant. So basically, there are another set of results that are presented into this research that describe the results of this option. So in this case, the global warming potential benefits from the fact that steel comes from a power plant that uses mostly renewable energy and zero carbon energy. From the point of view of the embodied energy, this has a much more limited impact because the energy that is needed to produce cement or to melt the steel is, of course, constant. So you will see all the results in this publication and in the paper that is presented among the proceedings of this conference. But I think that there are some interesting things that I want to discuss. First of all, transportation of construction and demolition waste is not impacting that much on the life cycle of a tall building. So actually, the transportation is described, the impact of transportation is described by the difference between these two numbers and the difference between these two numbers, which is not that relevant. What does it mean? It means that if you find a good supplier of material, even if it's farther away from your building site, you can trust that the saving during the production phase, so during this part of which is 95% of the environmental consequences of the production of a material, that impact, the impact of transportation is quite small. So you can buy your products farther away if you can prove that they are better than the local products. That's very important because that's one of the outcomes that we did not expect to have from this research. We thought that the transportation was quite important. The other thing is that the use of material, which is responsible of by far the largest crunch of the environmental consequences, yes, depends on the fact that a tall building is tall. It's a tall building, it's tall. But mostly, if you flip through the pages of the paper and of the publication, you will see that in some cases, the horizontal structures of the buildings that we consider, so the beams and the metal decking or the concrete slabs that form the horizontal partitions of the building, represent up to 80% of the total quantity of materials. And consequently, if we can find a way to design buildings that don't use all this material for the horizontal surfaces, if you can find a way to optimize these, to have shorter spans or to build long spans but with less materials, then we can achieve much more sustainable buildings than if we decide to cut our building in half. So of course, Fazlur Khan was right. There's a premium for height, but the premium for span is much more important than the premium for height. Some consideration. You can see from this graph that represent the number of papers published in peer-reviewed Journal of Architecture and Engineering that LCA is the new kid in town. So in 2013, there has been 250 papers. Just 10 years before, there were 30. This means that the science is still evolving. We've been talking about the expansion of gases or about the gravity of Earth and these kind of things for centuries. We've been talking about life cycle assessment for less than 20 years among architects and 30 years if we consider all scientific disciplines. And in this case, A lot of research has to be done, and a lot of this research can be carried on and promoted by the tall building industry. We are huge players in the field of construction, so we have the possibilities and the willingness and the interest to carry on research in this discipline because it's very important. If you want to sell something that is sustainable, it doesn't mean that this has to consume, it doesn't just mean that it has to consume a little bit of energy during the running phase, but also that it has to have a low embodied energy. Another very interesting point, there are several future research aspects that I would like to mention you. First of all, as I was saying, spans are responsible for a very considerable amount of materials. So if we need to explore the real needs for tenants, because ultimately they are the one that use the buildings, for tenants in terms of column-free structural space in buildings and tall buildings. Everybody knows this photo. I see all the architects and most of the engineers nodding along. Is the National Gallery of Mr. van der Rohe in Berlin? No, it's not. This one is the National Gallery of Ms. van der Rohe in Berlin. The lower one is the actual building with a very, very long span. The other one is an academic exercise that I present to my student. He would have made the history books of architectures anyway, even if he had a couple of columns in between. But he would have used less materials, still in this case, but less materials. We can study the optimal interstory height of tall buildings. This may lead to a significant savings in terms of building materials. Aon Building and John Hancock Center, both in Chicago, exactly the same height. The Aon Building has 83 stories. The John Hancock in Chicago has 99 or 100 stories. So same height, but 17% more usable floor area. We can investigate on the possibilities for specific application of modular prefabricated steel elements in building. I'm sure every one of us was amazed when we saw the guy in China building his 30-story tower in 15 days. Well, this means that he will be able to demolish his tower in 15 days, or even a shorter time. So when we build our building, we don't have to think that they are going to stay there forever. Of course, yesterday we went to the Empire State Building, which is 75, almost a century old. But most of the other buildings, those that don't have an iconic value, will need to be demolished sometime in the future. After 20, 30, 40 years, facades are old, so we're going to see about this later on. But then they become old, they have a functional obsolescence. They were designed, as the case of the Ritz-Carlton in Singapore, as a hotel. Hotels are not needed in that area anymore, so the building was not transformable into something different, and it was demolished. If that was planned through, if the construction was modular so that things can be just unbolted and lowered down to the ground and eventually reused, that would have saved a lot to the environment. Then, the speaker after that, the research on the demolition techniques for tall buildings. That's a fundamental thing. Again, tall buildings are not supposed to stay there forever. There has to be a clear and clean way to demolish buildings. Putting a crane on top of the building and starting to do things and dump the debris through the shaft is not the right way to do it, because things can fall over, it can be dangerous, it creates dust, it creates pollution, it creates noise. So there has to be a better way to demolish building. We don't have the experience, those guys have the experience. So why don't we start to ask them to prepare a demolition plan straight from the design phase of our buildings. If we know how to do it in 20, 30, 50 years, it's better. We can study, again, getting back on the topic before, we can study a flooring system in order to identify solutions that can save construction materials. If you're going to have the same span, but cutting in half the amount of materials, fine. Everybody's happy, the tenant is happy, the client is happy, the environment is happy. Let's try to optimize, yes, the vertical structure, because we are talking about tall buildings, but also the horizontal structure. again, the reuse, the demolition, the reuse and recycling of materials, and the study of what is the role of cement substitutes in the creation of concrete. Also, a steel building has a lot of concrete because of the flooring system. So if we can make that steel building, if we want to make the steel building more sustainable, we need to have a more sustainable cement. I just wanted to thank all the researchers that were involved and all the, as I was saying, the people that supported CTBUH in this incredible study, not just those that contribute in writing some of the parts of the final publication, but also the many companies that supplied us the information that were required to have reliable inventory of materials. So from the engineering companies to the demolition contractors to the suppliers of materials. Thank you so much.